Today I'm going to talk about Leetcode 54201 matrix. The problem is that given a matrix consists of 0 and 1, find the distance of the nearest 0 for each cell. And the distance between two adjacent cells is 1. For example, here, for this input, for every 0 we have the distance is 0 of course, and for 1 we have found that the nearest distance to 0 is 1, so we output as same as the input. For the second example here, we have this for 1 here, and all these 3 ones and has distance 1 to the nearest 0, and for this one we have the nearest distance to 0 is 2, because we only allowed to traverse from 4 directions: up, down, left, and right. And we also assume the problem is valid, that is, there is at least 1 0 in this problem. Let's have a look at the first. It's easy to come up with one idea, that is, we traverse from each value 1 to every other element in the matrix. We can use DFS or BFS, both work, but to calculate the short distance is easy to code with BFS, because we can only need to traverse how many levels, and each time we arrive the levels, that is the short distance. And for each BFS, it takes m times to get it, and because we have to travel each element in this matrix, so it takes m times n times m times n, so it takes m square times n square. That is huge. Another, that is, we can optimize a little bit further. That is because it is 0, so we do not need to call the DFS or BFS again, but the time complexity is still the same. That is worst case, but this works a little better for sparse matrix that has lots of 0. The third method is that we can continue optimizing it. That is, we find that we only need to traverse from 0 and call the DFS as like that. Here is we start any zeros as source to traverse to the other element. Here is that we have 0 and 0 traverse 0 0, we will not need to traverse, and for this 0 when we traverse here is 1, so the distance is 1, and the updated distance is 1, and we update this distance is 1, and we update this distance here. This is because when we traverse all the labels are 1, so the distance here is 1 plus 1 is 2 here. So in this way, we can only need to traverse with one BFS or DFS. So the time complexity is m times n. This dramatically reduces the time complexities. And we can also find that we can solve with a dynamic program, because here that is we find that the current these values. If we already know these values around labels, we can update values. For example, here the values around labels 0, we know that the distance is 1 here. And for this one here, if we have already updated the nearest labels, the labels are the distance is 1, so we could get the minimum values of 1, that is then plus 1 is 2 here. In this way, we construct a dynamic programming. So for each current index, the source, the distance to the nearest 0 equal to the minimum values of these 4 labels plus 1 here. And we found that we have to traverse twice, because for this test case, we can traverse from the top left to the bottom right, and we can get the answers. But for this test case, if we traverse from top left to bottom right, we cannot get the answers, because we will never update these 1 values. So we have to traverse again from the bottom left, bottom right to left, and bottom right to the up left. So we have to do twice traverse. The time complexity is also big O m times m. Here I'm going to write the code in BFS with the third method, and we can also use DFS and generate the time complexity for BFS and DFS are the same as big O B times D. B is the level, the number of branches for a tree or graph, and D is the depth. And the one difference I think BFS and DFS is generally for BFS the space complexity is space complexity for BFS is big O B power D is the same as time complexities. But for DFS, because we traverse the one depth, then go to another the depth again, so it only takes B times D. So this is the one difference for the BFS and DFS. Here I'm going to write the DFS first, which assume we have a function called DFS helper to traverse the BFS to get the updated the result here. Later I'm going to define these functions. And then we write a body function here. If what happens if we have to consider some corner case if the matrix is empty, then we return the empty array, and we take the height and width of the matrix. We define the queue. We have to put all the zeros in the queue. So we define the short path, the distance answers here. That we have the same array dimension as the matrix. So here we have the initialize the SP answers. If the matrix kind value is 0, we have to put it in the queue as the source for BFS traversing. Here, I put the tuples here, and 0 is the shortest path for to the source. Then if it's not 0, we can update it, initialize it as maximum values, and then we call this function here. We can update the functions in this array, so we can have the matrix array and also queue and also answers. Then we return this the short path is the answer array. So in this BFS function, we have to update this short path with the given input queue and matrix information. So here we have to call this function here, and which is m, n, and also q. The shortest answer here. So we have to check whether the queue is empty. If it's not empty, we continue to traverse with the queue. So first we dequeue the element here, and we get the position and distance. So current index I is pos 0, index j is pos 1 here, and we traverse to the traverse is for labels here, or we can find the for labels here. 1 0 0 1 0. This is 4 directions of the labels. So we can get the new positions. And we have to check whether the new position is in the boundary of the matrix. And then we have to check whether it is visited or not, because here we didn't define a matrix to mark whether it is visited, because so we can utilize this array. It has only 0 and 1 matrix here. If the current value is not visited, that means that is still equal to the initialized value. otherwise it has already validated. If they can be validated, so we put it into the queue. And updated the values. And also we update the short path distance values. +1 here. And if we finish it, we should have updated all the values. So basically this is the idea for BFS. Let me check the code. Oh, sorry, here that should have some semicolon. What's going on here? Something is wrong here. Something is right. What's the problem here? That is not subscribable for 2019. Let's float x. Oh, here there's something wrong here. Let's read ing. It's a matrix, not a single integer variable. Okay. Then we check the other case here, 0 and 1, for example, whatever. Good, we made it.